Hello, I'm John Sciavacco, the co-chair of the NY-GEO 2023 conference and a board member of the New York Geothermal Energy Organization. I'd like to welcome you to this recording of a live presentation from the conference, a two-day event which was held in Albany, New York on April 26th and 27th of 2023. This year's educational sessions and keynotes represent the latest in ground source heat pump system design, product innovations, and installation practices, along with important policy, regulatory, financing, and incentive updates. This presentation is one of over 40 sessions from the two-day event, all of which were recorded and available at NY-GEO's website, www.ny-geo.org, along with session descriptions and a link to download the slides from each of the sessions presented. NY-GEO is proud to make this content available to our members and other industry stakeholders, and if you are a member, thanks so much for your support and participation. If you find this content valuable and for some odd reason you are not yet a member, consider joining NY-GEO at the appropriate membership level with details available at our website. The live recording from the NY-GEO 2023 conference will start in just a moment. Thanks so much for listening.
Okay, hopefully you can find a seat. We've got extra chairs. Welcome to the Zero Place case study of new construction multifamily. I think consistent for those of you that were at dinner last night. This project is a primary example of utilization of the Einstein quote of we have to think differently. And the team is going to walk through the details of the design of the project as well as how the business is performing, which is exemplar. And I would just say I would use this as a case study benchmark of the art of the possible of a net zero mid-rise mixed-use building. I think that sums up the project pretty well. So with that, I'm going to turn it over to Jens Ponikau with Buffalo Geothermal. Okay, so
Pasquale, you, yes.
We're going to start with Pasquale Strocchia. Strocchia. And Pasquale is with Integral Building and Design as an energy consultant for the project. And then Jens will present after that. Is that correct? Or Hugh? Hugh is going to be presenting after that, and then I think Jens is going to be last. I think I got that one right. So I'll turn it over to Pasquale. Excellent.
Thank you. Great to see everyone. This has been a year in the making. The project was completed back about a year ago, and occupancy had started last spring. So this building that we'll be talking about is now very close to a year's worth of data. So we're really pretty excited to be able to share it with you. So Zero Place. Brainchild of three individuals. One of them is here, Anthony Abbey, is a part member owner of the building. The vision was basically a carbon neutral building, all electric, and it includes 46 apartments, a mix of 1 and 2 bedrooms, including some affordable housing units within there, and then amenity spaces, and then 6 retail spaces. So there's our timeline of when it broke ground. Got a bit slowed down through COVID, but made it to the goal line. And again, the apartments have been fully occupied since pretty much the end of May, early June of 2022. Just a couple quick shots about the interior and the exterior of the building. There were a lot of other features in addition to the geothermal that were integrated into the project. But we're going to, for this presentation, really just focus in on the geothermal. Zero Place was one of the first projects awarded to NYSERDA's Buildings of Excellence and to serve as a model for carbon neutral building. In terms of the building strategies, it was actually quite simple. Starting off with a very high performance thermal enclosure, an ultra efficient geothermal system, and then optimizing a solar PV system for renewable energy. The thermal enclosure was consisted of ICF wall assemblies all the way up to the roof line. So that was 4 stories plus a penthouse. And thermal bridge-free construction, triple pane fenestration, high-R slab, and fully insulated roof. Putting all that together, they were able to achieve very aggressive air tightness detailing. In terms of the whole enclosure, the tightness was about 0.6 to 1.0 ACH 50. And then there's a compartmentalization test, which is air tightness between apartments was also really quite tight. So obviously the heart of the building in terms of its mechanicals is the geothermal system. I'm going to leave that to Jens to talk a little more in detail about how the system was designed and installed. These are just some shots about, for the well field, 15 boreholes. We've got a total of 64 heat pumps in the building, totaling about 94 tons of rated capacity. And that includes not just space heating and cooling, but also an integrated domestic hot water system. Again, Jens will talk a little bit more of that integration and some of the values of it. The key thing that I'm going to be getting into in terms of overall energy performance is that we were able to get the domestic hot water down to about 10% of the total building load. So this is a centralized domestic hot water system, and I think that was really quite, actually a very inspiring result that we came up with, because in many high-performance buildings, they're still looking at about 1/3 of the energy going to domestic hot water. So getting it down to about 10% was really quite an achievement. Again, some other design features that we'll be talking about later. What I just wanted to emphasize is that in terms of the design, even though the New York Clean Heat program allows up to 85 watts per ton, this project was designed for all its pumping power to about 15 watts per ton. The solar PV system, again, just to give you a concept, pretty much the entire roof is covered with PV. It's a pretty cool shot of what that looks like, as well as on the south side, solar awnings were added as well, helping to reduce the solar heat gain on the south side, as well as increase the solar production. In terms of the monitoring, this is just a bit of an outline of the kinds of data that was collected and continues to be collected all in real time. So besides energy use and solar PV, each apartment is monitored for its energy use, including the heat pump, the common areas, all monitored, as well as the commercial spaces. What we're not monitoring is a whole bank of EV chargers, which is on a separate utility service. So here are the results. Based on 10 months of occupied data, the total energy use for the building came out to 280 megawatt hours for the year, and about 93% was covered by solar PV on the annual basis. So just a little shy of the target, leaving us some opportunity to begin to tweak the building operations to see how we can kind of get closer to that net zero. Now, one of the things that is also valuable to appreciate about the building is that in terms of the actual performance before solar PV, the energy use intensity of kBTU per square foot came out to just under 17 kBTUs per square foot per year. So the passive house standard is approximately 15 kBTU per square foot. Interestingly, at a recent conference, there were a number of projects being described that were passive house certified, but when they were monitoring them, what they were coming up with, I believe it was 20, 25, and even 30 kBTU on a measured basis. So, then now the presenters were chalking that up to, well, occupant use is a big variable you can't model for and so forth. So I would say the fact that this building is achieved, in the order of 17 kBTU per square foot is really, again, an achievement, all human factors considered. In terms of the breakout between how the apartments and the common areas energy use was, we've got certainly, the large majority, or about 64%, 63%, dedicated to the apartments, with about the balance of 37% of the energy dedicated to the common areas. Now, to give a clear idea of, so the owners decided to have a master metered configuration. So all of the apartments and all of the common areas are on the building owner or landlord meter. And the pricing structure for rent is an all-in model, where the tenants pay one fee, which includes their rent, their energy, their water, their cable, their phone, internet. It's all a package. So one of the ways that they have a backstop in terms of energy use is they have explicit restrictions for commercial uses within their apartments, as well as having kind of I don't want to say an allocation, but a kind of a threshold limit on an annual energy use per year. So, so those lease allowances were for one-bedroom apartments for 4,300 kWh per year, and on the measured basis, the actual average came out closer to 3,200. And then for the two bedrooms, significantly below what the threshold was put. Now, in the lease, the way they have it structured is that if you go above the threshold, then you just pay a flat fee, like $50 for 10% over, or another $50 for 20% over. So it's they didn't want to start getting into a billing basis of kilowatt by kilowatt hour. So, but in general, the building is performing quite well, and the vast majority of all tenants are kind of within their target for energy use. Or I shouldn't say target, but within that threshold. In terms of the GEO system, so there's, this is obviously a pretty exciting piece for us here at the conference. Again, we have one common loop, and then we have all the space heating and cooling happening off of that loop, as well as the domestic hot water. And so a couple key pieces, the total energy is, for the GEO system, is about 106 megawatt hours for the year. So the other balance, the 173, is all other building uses. So of that, of the GEO, the apartments are taking up about 26% of that energy, and the domestic hot water, the domestic hot water is just under 30 megawatt hours per year, or 11% of the total energy use of the entire building. Loop pumps, 3.64 megawatt hours per year, or just about 1% of the total building energy. So so from our experience of working on a number of multifamily buildings with geothermal and seeing the typical 10, 15, 20 horsepower pumps, three-phase, and so forth, to be able to see these results, it was really quite staggering. And I'll just end with these last two slides, which is to kind of highlight one of the greatest concerns that we had. This was about peak demand. So in the summer, during the hottest day of the year, the hottest temperature we recorded, close to 100 degrees, there was a overall demand or energy use of about 71 kW. Actually, and that was after hang on. So right here, you could see that there was no solar production at that time. So it was hot all day, and then people came home, and appliances were begun to be used, and maybe the air conditioning was bumped up a little bit, and the domestic hot water was actually part of that peak as well. So, for 46 units, that's a pretty extraordinarily low peak. In the wintertime, at a -6 degree day, there was a peak coincident with the coldest moment of that day and this past year. It was about 49 plus kW, again, without any solar production to offset it. But it was later in the evening at around 5 o'clock that the greatest utility demand occurred during the winter, which was 65.5 kW. So there's been a lot of talk about thermal storage and how geothermal could make a huge difference in the concern about winter peak. Well, here's showing that this building, at least, is that the winter peak is actually still lower than the summer peak. So, and with that, maybe I'll end and turn it over to Hugh. And we'll take questions after all three of us.
Okay, great. So I'm going to show the results from this, and really I'm focusing on the thermal side of the building, and Pasquale just told you about some of the energy use things that are going on. And just a review of the specs, I think, so the only thing, the thing I really want to focus on is that the geothermal loop was used for space and water heating, and so, and really, so we've monitored that once in the past at a hotel years ago, and we saw that it's a very positive thing to do because it makes the loop smaller, because the loop is sized for cooling, and if you're extracting heat year-round, now when you do domestic hot water heating in a building with a big DHW load, it's going to have a big impact. I think everything else, Pasquale had covered. Here's another picture of the one thing about a mechanical room for a geothermal building, it's kind of underwhelming. There's no mechanical stuff in the mechanical room. There's a lot of pipes. But, so there were loops on both sides. In the back, those are the domestic, the water-to-water heat pumps that provide domestic water heating. And the central loop pumps, as Pasquale said, that it wasn't 10 or 15 horse, it was 3 horse or 2 horse, and it had a very low pumping power. So here's kind of a schematic. So NYSERDA had got involved because they were interested in this aspect of the geothermal loop and adding in domestic hot water and what the benefits of that are. And so the building was already going to measure power. And so what we did was add some thermal metering here. So I won't do that. But you can see, so the red dotted boxes are the BTU meters that we added. And so we added a BTU meter on the ground loop so we would know the heat extraction and heat rejection rate. And we installed a high quality BTU meter to get a very accurate reading of that. And then we had 2 BTU meters on the domestic hot water system. And we had one measuring what hot water was delivered to the building. And you get that by measuring the cold water in. There's a lot of water flowing around and returning, but what you use is the cold water going in, so we had a flow meter there. And the thing that we did at this building that we've only done a few other times, we also measured the recirculation losses. And so that is, you send hot water out, and there's, in multifamily buildings, there's always a recirculation pump that basically pumps hot water, makes sure there's always, that the hot water header is always full of hot water. And so that actually makes this, so there's always hot water at the tap. and we measured that as well. We added a couple other sensors, but those are the focus. And if you look at the box with COP, so we could figure out the COP of the overall system by measuring the recirculation losses and also the heat delivered, and those two summed together is what's delivered by the heat pump, and then we divide by the power and get the COP. So here's some of the energy results, so kind of focusing on the HVAC. So the box in the upper right is kind of, so I was involved in some work when NYSERDA where we had basically expected energy use for a new multifamily building. That's what's listed up there. And we probably, and of course that baseline building had a gas heat system. So we displaced in theory about 17,000 therms of use. Space cooling, we actually saw a little more space cooling use than this. And actually one thing that's kind of known in multifamily, as the building gets tighter and tighter, you actually start to use more for cooling than you do for heating. And heating and cooling in terms of heat pump energy use were pretty equal, and probably cooling is going to work out to be a little higher. So the bars show the percentage of the electricity use going to the space heating heat pumps, the domestic hot water heat pumps, and the pumps. So the pumps in this building were extraordinarily low. And so in many, best practice is usually that the pumps are about 8 to 10% of the heat pump energy use. And if you're doing, and so there used to be limits in some programs on pumping use on that order. We are, 5 times lower than that, 3 to 5 times lower than that, and it depends on the season. And it was designed for a low peak pumping power, but the variable speed nature of this actually did pretty well. So the other interesting thing, so the pumping system here is what I call an open loop pumping system. In a traditional commercial building, you might have a differential pressure sensor out in the building, and you might measure the pressure delivered and have a variable speed drive that is controlled off of that. The reason I call it open loop is that it's all built into the pump, and the pump doesn't measure anything. It has a built-in pump curve, and it can respond. And I think, and I always theorize that control might not be as good as having a sensor, but I think we exceeded our expectations. In commercial buildings that have had traditional VFD and a pressure sensor, I've actually seen we've never got as low as 2 or 4%. So the annual mechanical energy, so this is both domestic hot water and space conditioning, came out to be 1.8 kilowatt hours per year per square foot. And as Pasquale said, that the whole building is 5 kilowatt hours per square foot. I don't speak kBTUs per square foot because I never use K with BTU. I was trained never to do that. But and then the multifamily part was about 1.4 kilowatt hours per square foot for space conditioning. So again, everything was surprisingly low. So the ground loop did what you would expect. It performed. This is a supply temperature over more than a year. In the early spring, the building was just starting up. It had mixed, it wasn't fully occupied. But you can see the main lesson is that the loop temperature at the end of the first year got back to where it started. Good sign. And then so the winter loop temperatures rarely dropped below 40, and in the summer loop temperatures rarely got above 75. And the loop started out right where you would expect a far field temperature to be, around 50. So, so no, so this is, so if a geothermal is working properly, it's not very exciting, and this one is not very exciting. I don't want to say boring. But so here's the energy use trends for the heat pump. So a little busy here, but the takeaways are that as expected, we did use, so the peak days for energy use, this is daily data, were in the winter. So the cold winter days was when we used the most. And the energy use, so we did see in a geothermal building, in the beginning of a season, you ought to see less energy use because the loop temperatures are more moderate. And at the end of a season, the loop heat start to build up. You want to see slightly more energy use. We did see that. So the peak day was not a cold day in December, which is the upper star, but the highest energy use day was late in the season in February. So, just like we expect for a geothermal system, things do change across each season, but no real surprises. So the other kind of surprise is that lots of mixed operation at moderate conditions. So when you're around 60 degrees, so we never dropped. So if so this implies the fact that the energy use never went to zero on a daily basis implies there's lots of mixed cooling and heating going on. And actually looking at the heat pump operating patterns, when you have 46 apartments, everyone is doing amazingly different things. I'm always amazed at how much variation there is between people. But in the end, it looks like our balance point is in the 55 to 65 range, and lots of simultaneous heating. So again, confirming as a multifamily building gets extraordinarily tight, you're going to have more impact of cooling, and cooling starts to become more important. Ground heat transfer. So here's again daily data on for the ground loop load. And so we actually had, this data starts about the first of the year. We had some instrumentation problems so that we couldn't totally understand the loop heat till after the first of the year. But the interesting thing, so the line on the bottom is the extraction of the water-to-water heat pump at mild conditions. And so you can see it uses about 0.7 MMBTU per day when in the swing season. So if you extract these points down, it implies that our balance point for space conditioning is probably about 60 degrees where it should be. And so our peak load, and Jens is going to talk about this a little load. So the peak extraction rate we ever had was 5.7 million BTUs per day. And that was at an average outdoor temperature of 15, because this is daily data. And from this, since I know heat extraction and power, I can infer that the COPs for the entire building, space and water heating, was over 3.5. Oops. Previous. Okay, so now I'm going to focus. On the water heating system. So actually. This has 2 water-to-water heat pumps, and actually they're configured, and there's actually 2 stages of tanks. There's what I call a preheating stage, and there's a final stage. And the recirculation water actually comes back between the tanks. And this is important because that recirculation loop is running all the time, and if you just had a single tank, you would have totally disrupted the thermocline in the tank, and it really would have hurt performance. And when you have a preheat tank, you have much lower temperatures coming into the heat pump, and it works better. And so the heat pumps were configured so that one heat pump could serve the top stage or the final stage, and one could serve the preheat stage. And there were provisions that they could switch, and there were provisions that they could all do the final tank if it was needed. And so here's what actually happens. So if you look at the bottom graph, my heat pump 2 is what serves the preheating stage. That's blue. My heat pump 1 serves the final stage. And so first thing you see, so if you're on a preheat stage, the heat pump comes on, runs a long time, turns off. For the heat pump serving the top tank, it's always got 100-degree water coming back to the tank, and so it's always disrupting the thermocline, and that heat pump cycles a lot more. And if you look at the top graph, it's the temperature. So the bottom 2, the purple and the blue, are for the heat pump that's serving the preheat stage. So that's seeing a lot colder water come back to the heat pump, so it's more efficient. And if you look at the green and red, that heat pump always saw 120-degree water coming back. So this is why if you're going to have heat pumps, you have to think about this and have 2 stages, and your preheat stage is always going to work a little better. Here's the COPs for the high stage and the low stage and the average. So actually the high and low stage COPs are inferred from manufacturer's data. The one in the middle is the measured. And so the COPs, just like you'd expect, the loop gets warmer in the summer. So the heat pump doesn't have to work as hard, and the COP goes up in the summer. And in the winter, it's a little colder, so the COP goes down a little bit. And the high temp, the heat pump serving the preheat stage has a COP of 3.7. The one serving the high stage that cycles a lot and has hotter water has a little worse COP, but the overall average COP was and we're coming up with 3.25 for an overall average. And that's pretty good and probably better than you could achieve with any air source commercial water-to-water heat pump. So again, to focus on water heating a little bit, because I think that was a pretty important part of this. The average use for this building it varied a little bit across the year, but by the time you got to June, the building was occupied. We were using 1,200 to 1,300 gallons a day, which is, which comes out to 18 gallons a day per bedroom, which is about where we expected it to be. The other interesting thing is that, so I've been involved in monitoring in other domestic hot water systems, and one thing that we've been seeing is that peak flows in multifamily buildings are much lower than code assumes and people expect. So the highest flow we ever observed in a 1-minute period at the 99.9% level was 6.2 GPM. We did have one event at 9 GPM. But this is why, so what's happening pretty soon is current plumbing, and there's data from other buildings confirming this, so plumbing codes are about to change. And you gotta remember, the building probably has a 3 or 4 inch supply line going to the building. 3 inch. So a little big for 6 or 9 GPM. So you could, and again, this all adds cost, it makes losses higher. And I think one thing, and so plumbing codes, so IAPMO, there's work in California, and probably the changes will take place there first, but a lot of the calculation tools from ASHRAE and IAPMO are gonna allow people to take this into account and take into account the diversity. And really what it means is the odds of 2 people turning their sink on at the same time or taking a shower at the same time are not as high as people expect. And actually, so the other key thing, so in our measurement of recirculation losses, and this is consistent with other buildings, we've seen that recirculation losses are about 30% of the load the heat pump has to meet. So recirculation losses are a huge part of where the heat is going. And so, and of course it increases the load on the final tank and makes it cycle fast, as you saw. And really, and what I'm gonna show next is a little experiment, or in a couple of slides, I'm gonna show the impact of doing some changes. Here I just wanted to show this, that, so we were supplying 120-degree water to the building. And if you look at the cold water line, if you always look at the minimum, that's kind of the city water temperature. So city water temperature gets as high as the high 70s, and then it gets as low as 40 or 45. And like I said, we did, and so you can see, actually as a preview, you can see when we did some changes to the recirculation loop, our actually delivered hot water went up and our recirculation temperature went down. And that's what I'm showing here is that, so we did actually turn down the recirculation loop from 9 GPM to 4 GPM. And does anybody know why recirculation flow is 9 GPM? Because that's the only pump you can buy at the plumbing supply store. So we cranked it down and we got down to 4 GPM. And so there's a risk that, we might not have enough recirculation flow to maintain hot water everywhere. And if you look at the recirculation temperature, TR, it was still 112 degrees. So we still were good. And the savings we got from doing this were on the order of 20 or 25% just from making this change one day. And we probably could go lower. So, and we may do this a little bit in the future, but I think the flow could be 1 or 2 GPM, and you still would not be starving people of hot water, which is what you want. And I think, and the key thing is, these losses do not come from piping losses, probably. It's not just thermal loss from the piping, it's the disruption to the tank and the thermocline in the tank. If you're always flowing at 9 GPM, your tank is mixed. And in a hot water system, you'd prefer the tank not to be mixed. You'd prefer the hot water to be at the top and the cold water to be at the bottom. And over pumping just makes that a problem. So yeah, peak demand. So this is kind of the same thing that Pasquale said, but it showed, but it's focusing on the heat pump itself. So July 20 was the day when I had the highest peak use for the heat pumps themselves. And you can see the outdoor temperature was 90, and the water, and I give the demand of all the components. And the solar system was putting out, 10 or 15% of its max output, putting out 20. But, and so one point about this is, so I think everybody knows that solar, if you add solar to a building, you have not reduced the peak demand of the building. Peak demand of the building and the peak impact on the utility is still the same because the peaks always happen after the sun go down. And one thing that's interesting, actually, so the actual building peak happened later than the heat pump peak. Most people assume that a building peak happens because of air conditioning, but in this building, the building peak was not primarily driven by air conditioning. So very interesting in that sense.
It's where clothes drying, and there's a set of clothes washers in every apartment.
Oh, okay.
So that's
Yeah, so actually, Pasquale just reminded me that there's washer and dryer in every department, in every apartment, which makes sense, and that's why the water heating is kind of near what you'd expect for that. So, and here's the same thing on the coldest day. So on the coldest day, so my bottom graph, and I didn't say, yeah, so the middle graph is outdoor temperature, the top graph is what the heat pumps are doing, and the bottom graph is the building demand, and the black one is what you're drawing from the utility. So again, so with these heat pumps on a cold day, in the morning, we had not, the peak for the build, that's when the peak use of the heat pumps was for heating, but it was not when the building peak was. The building peak was later in the day, and again, solar had not much impact, but I think the key takeaway is that this building is not, so the peak demands from a building level are not happening because of heating and cooling, they're happening because of occupants and other issues. So kind of a takeaway on an MV thing, I think the ground loop is working perfectly. And the heat pumps, so the energy use of the heat pumps for both space heating and water heating were very low, and pumping was extraordinarily low. And I think adding, and so Jens, I think, and Jens is going to talk about this more, but so adding domestic hot water, you don't need to make the loop any bigger. So you actually can make it smaller. And I think Jens had proposed a deal to the owner kind of based on that logic, and we confirmed it. And so we're getting, and so the domestic hot water heating loads right where we expect, and we have a COP of 3.25, which is probably better when you get all said and done with an air source unit like a Sandin or other system that can do domestic hot water by extracting heat from the air, is probably going to be in the 2.5 to 3 range. And so we're doing a little better of that. And so the other thing is that, so the one thing, everyone builds good buildings, but all buildings have 30% of the energy use go to recirculation losses. I think Tatum at a building in Ithaca found 37%. So I think, and so our field testing of some sites in upstate New York on old multifamily buildings was about 30% too. So this is sort of the last frontier. If you want to make the building efficient, you should pay attention to the domestic hot water system. And I think that's it.
Yes, I want to just add a few things here. I mean, that's what we do. We design build those systems directly. We usually don't go through a spec and bid process. We actually, all the materials or the manifolds or the pumping integration, which makes all this efficient, we have vertically integrated in our company, and we actually pre-build them in that fashion. And we give people a fixed price. This is what's going to cost you. And we usually pride ourselves, unless you change the scope on me, there's no change order. So they already get a value engineering. So just want to highlight where this is. This is in the middle of the Hudson Valley. Very cold winters, very warm summers. And it's not just we call it zero place. Actually, the building is called that way. And it was interesting that this very quickly filled up because a lot of tenants appreciated the concept of having all the energy costs included. And of course, the developer wanted to keep that very low for him, and that's why they went the extra length here of it. And I mean, we just point out that the awnings here are also solar panels on the southern side. And that this is actually the elevator shaft, and they actually squeeze solar panels up there and everything that we could do to maximize that. So it looks like a spaceship from up above, and you don't see anything from below, but that's kind of the whole concept, to maximize this. Just to point out, Pasquale has shown some of the pictures. I just want to point out, these are only 15 boreholes, that's it. And they're not even 500 feet down, they're actually 400 feet down. And we could have put enough directly under the footprint of the building to actually have a 30-story building above it and still have it all within the footprint. So that's really the take-home message, that we can do this now. We start to learn on how to squeeze more BTUs out of it and actually do that in really, really, really large buildings. And, looking at the tonnage connected to this, we're at 67 feet a ton. So normally it's like 200 feet a ton or 150. That's kind of, people consider borderline. Look how well this performs and how little actually the infrastructure is. But that's what we're trying to do. We're trying to value engineer that from the get-go and get actually data from this and stream live data so we can learn. All right, water furnace heat pumps in this project. And Hugh has already touched the stage design. That's kind of a thing from us where we thought about how can we improve actually how can we actually improve the performance of it. One thing he pointed out, it was weird when I come in and say, you know what? Let's do the hot water too, and I give it to you for free. And everybody goes like, what are you doing? No, I want to have the hot water there because I need it to cool the loop in the summertime. And that allows me to make the loop smaller, and the money I save with this, I can buy all the equipment and give you hot water for free. Whoa! This is too good to be true. Okay, let me do this. And that's what we did. So the whole point is that we get the average pumping power down to about 400 watts. Normally, I've seen systems, and I'm sure you have, where you have a 2,000 square foot home and it uses 400 watts for pumping power, correct? 2 2699s. That is 250 watts. This entire building doesn't use more on average. And there are 60 heat pumps on there. No balance valves, no flow restrictions. Focus on efficiency. Get your pumping power down. And obviously the key is the variable speed pumping, where the pumps control themselves. They sense on how many heat pumps are online by measuring the back pressure. A valve opens up, a pump turns on. The pumps in the basement sense that, and they speed up and down based on that. And that's really the key. So they know exactly how many pumps are operating and how much water flow is needed. And they throttle back when they're not needed. And just to emphasize, there's no backup heat. There's no electric heat element in there, in the whole building. And the only gas, they have a gas line that goes to the emergency generator. That's it. It's not even entering the building. So the entire building is completely emission-free. that's what you was, this is one of our graphs here. And the hot water is really the key to actually make the system cheaper. And that's what we come up with. This is the final tanks, and you can see it's more, the final tanks only, go from about 100 to 125 degrees here. And this is mainly the return water from the circulation pump, why this is cycling. So this is about 5-hour period. It turns on every hour for 10 minutes, 15 minutes to bring it up to a certain temperature range, but that's it. The heavy lifting is done by the preheat tanks and from the preheat heat pumps, and they're exposed to colder water. The water they're seeing is anywhere between, you see that here, this is a preheat tank, whenever there's a big water draw going on, but normally they are running around 100 degrees or 110 or 104 degrees, and that allows us to operate at a much higher efficiency. And then we have to bring the water up to 120, but we only doing that we only doing a 20-degree lift at the max with the second stage. So yes, it's less efficient. The heavy lifting to bring up water to 100 degrees, 104 degrees from 45 or 50 is actually done at a much higher efficiency that way. That's the trick. Now this looks like a terrible graph, so let me walk you through it here a little bit. This is looking at different portions of the building. This down here are actually the water-to-water heat pumps and what they do to the loop. The blue ones are actually on the northern part of the building. The green ones are in the middle portion of the apartments, and then the red ones on the southern side. And you can see this is, excuse me, this was actually, in the winter here, that was actually in February, where some of the apartments are operating in air conditioning mode on the southern side. It's a sunny day. And, this is the 0 degrees here, and some of them are actually rejecting heat into the loop field right now. Actually, the southern portion of the building and the middle portion of the building are rejecting heat. The northern part of the building is taking heat out, and then once in a while, hot water heat pumps turn on, and they take a lot of heat out. But overall, so they're exchanging heat between each other. The loop field doesn't really is very affected by it. So that's the art. We don't waste anything in air conditioning mode by rejecting it into the atmosphere, only to turn the boiler on next door to make hot water or to heat another apartment. That is part of the value proposition of geothermal. And I point out, this is again the average loop field temperature, similar graph what Hugh has shown you, but I want to point one thing out. We are rejecting thermal energy into the loop field, and we're creating a storage reservoir of thermal energy. And I talked about this yesterday, and this documents it. We're going up, every single BTU gets actually brought into the loop field and stored there. And we can measure this, and we can actually then also measure how much we're getting back during the heating season. And we also see that it stabilizes here. We're not into phase change yet, but it's extremely stable during the winter time. This is actually now just looking at what the building is rejecting or extracting. This is about a 50-hour time period, right around the peak time of the year. And you can see even then, we're starting rejecting some heat into the loop field, but then we're starting to suddenly get a lot out of it or more. It depends on how many heat pumps are operating. That thermal battery is reacting to input and output. It immediately reacts to it by increasing or decreasing its delta T. And that's how it delivers more energy or less, whatever you need. When you have a battery which delivers as much energy as you need, and it actually does that, this is essentially for a 48-hour period, and we can measure that now. It gets colder, it increases automatically its delta T and gives you a constant thermal energy back. It acts essentially like a grid battery, balancing the grid. That's how it acts. How much is that worth? And I gave this slide yesterday. So during the peak, absolute peak time, we pulled about 106 kW from that thermal reservoir. And the peak hour was about 90 kW hours. How much is that worth? Because it directly avoids any storage in the electrical grid, because it reduces the battery storage we would need otherwise. And the point was, NYSERDA published this report that we're currently paying about 567 kilowatt hours for grid storage per kilowatt hour. Well, during the peak hour, we avoided 90 kilowatt hours from the electrical grid in a certain way. So we avoided $51,000 worth of grid storage. Now, how much was that on a peak day? We avoided the equivocal of almost $1 million. What it would cost otherwise on a peak day, if you have an air source heat pump running at a COP of 1, that's what we avoided. That's the energy the alternative is to create this kind of grid storage. And then this is a peak month. This was now from January 11th to February 10th. That was that amount. Now, is this realistic? Well, you could argue, no, we don't need a month of storage because we can recharge that. And we can also, well, what are you going to do if the sun doesn't shine or the wind doesn't blow? How much storage do you need? A day, 2 days, a week, a month? Now, this is only the storage. Now, add to that the fact that we now don't need the power generation to recharge it. So avoiding the power plants or the windmills or the solar panels. One thing is certain, this is happening at 7 or 8 a.m. in the morning after using an entire night to heat the building, and then the peak occurs. Every 4-hour battery or 8-hour battery will be depleted by that time. This is a battery which is there for 6 months, and you don't have to recharge it, and it acts like that. So just a very different way of thinking about it, but we're pulling a huge amount of BTUs out of the ground, which we injected a few months before. That is really one of the key concepts here. And it avoids a huge amount of electrical storage doing that. I want to thank a few people. First of all, NYSERDA. That was one of the buildings going through the initial geothermal rebate program. And Hugh is actually the energy monitor, the go-to guy for NYSERDA to monitor those systems. So we had designed the GEO system where we tried to do everything early on to make sure we do it as convenient for them to monitor it. We had the sensor walls built in. This is why the pipes look a little awkward there, because we had to make sure we don't have any kind of flow disturbance, etc. And this is very, very important because it shows that heating and cooling might not have to have an impact on the grid. What does that mean? Right now, the entire load for all the buildings in New York State, the heating load, the peak is about 123 gigawatts. That's how much gas we're using, and that's a published number from NYSERDA. So the thermal load of the building is the peak. If we're converting this one-to-one to electricity. Now, we save through heat pumps, we shave that off a little bit, but it's still an enormous load. This building demonstrates that we might not have an impact on the grid if we're doing it right. That's why this is important. And this is why we wanted to have NYSERDA officially monitor this. We didn't want to be associated with the data to make sure we're not biased. But that way they can use it for policy decisions based on that. So that's the important thing. So this is going to be beyond New York State because Massachusetts and Maryland, they're all in the same boat. They're trying to convert a huge thermal load, which has been served by gas, to electricity. And that's going to be interesting. But it can be done, and this demonstrates it on a larger scale building. So the utilities, they love us giving them 15-minute data on the entire building to understand the load profile, the impact, the peak impact, etc. We already submitted that to DPS. They're testing their rates, their new standby rates on the impact of this. The data is a treasure trove. So I have to thank Pasquale and you for that, helping out and being the guardians of reality in a certain way and make sure this is legit. And it's coming essentially from NYSERDA, not from us. Also, big thanks to WaterFurnace because they actually supported all this, and they supported not only giving us variable speed technologies for some of the heat pumps, but actually they built the monitoring system for the heat pumps into the units before they shipped them. And they provided that in kind. So on a side note, this is actually giving some remote controls here for the tenants, obviously, to control their thermostats, etc. But I mean, this is why we have a treasure trove of data and can really see it in a granularity, and we understand what actually is causing energy use, etc. So that's the important part. Thank the project team here. This is not just me, that was a whole enthusiastic team to say, let's show everybody what can be done and what the result of that is if we're doing everything right. So this has really worked out well. I think to demonstrate that, again, we won't have a peak impact. The grips will not collapse if we're doing this right. So this is not only that we say it, but we monitor it, we measure it, we're staying away from the data, we let the state do it themselves and confirm everything. That is the impact. Anyway, I'm going to be quiet now and let JR do his magic.
Okay, we're going to test the dilemma between your curiosity and your hunger. So great job by the panelists on all the data that's been collected on this building. Truly makes it a unique envelope, a unique structure, and the performance is stellar. So go ahead, Matt.
Very well done, guys. Just curious, how was the projected utility cost for the tenants calculated? Did you use this expected COP of the ground source heat pumps, or was an equivalent code-compliant air source system used? Are you making money off of the bill that you're sending to the tenants, or is it essentially neutral for the owner?
So I can't speak for the owner, but in terms of the actual estimation was based on our energy modeling of the apartments, which included the published COPs of the equipment. So that's kind of how we advised them, and then we said, look, add 15% because you never know.
Toby Hudson, and I want to follow up on that for a second. Can we, I think the last slide indicated that the heating and cooling costs were borne by the owner and were included in rents?
Yes.
In that case, was there any metering? Do apartments even have their own electric meter?
No, they have a app that is tied into our monitoring system so that they can get a sense of how much energy they're using instantaneously as well as each month.
But again, all rolled into their rent.
Correct.
Fascinating. Can we, I have like a zillion questions. I can also follow up with you guys. I know where you live, at least digitally, some of them. Online, but can we go back to the green, the graph with, I think it was Pasquale.
Pasquale's pitch. Okay.
Pasquale's green triangle above the thing on the peak day.
Yeah, right there.
Yep.
So that's the winter peak.
Yeah, that's good. So what's happening in the building before the winter peak, right? So you've got that big green triangle.
That's solar.
That's the solar during the day. It was a sunny, cold day.
So just real clear,
Put the pointer where
dark-
you're talking about there, the mouse.
Yep.
I think it'll work.
Well, the dark red line is the total energy use for the building. The red shaded area is energy imported from the grid. The dark green line is the total solar generation. And the green shaded is solar energy exported to the grid. So the white is solar energy used during the load, to satisfy the load at that time of generation.
Got it.
So, so the net, in this case, for these days, would be total energy used minus the amount of energy generated.
So what this essentially indicates that even during the peak day, you exported energy into the grid because the building was not using that much.
Well, right,
Right?
but for this period, which I believe is, it looks like it's a 1 day or 2 day,
Right, that makes sense. Right, coldest day, coldest.
but there was still some energy purchased or imported from the grid. But the peaks, the key thing here, though, is that there's no solar happening during the actual peak.
Right.
And that the building's efficiency in terms of its thermal enclosure as well as the geothermal system really kept that peak quite low. I mean, for 46 apartments, we're talking about less than 1,200, 1,300 watts per apartment, so.
No,
So
very
it's
impressive.
minimizing
Thank you.
the-
Less than a hairdryer happening.
It was minimizing the daily peak load impact on the grid. That's your point,
But
right?
and the 15-minute, which is also part of the economic model, because the utilities charge their demand loads based on the highest 15-minute period, or the highest peak during a 15-minute period of the billing period.
Okay, we're going to take 2 more questions, so we'll try to see if they're quick so we can make sure there's sandwiches left for us. Yes, please.
So Bart from Aztec. First, I just want to quickly say, I feel like I witnessed history today. Like, what you all did is extraordinary for the whole country. And just, I did have a couple questions. Hugh had said that AC didn't drive the peak, but I didn't understand what did drive the peak. And then he also called it an open loop, and that confused me. So those were my two
Yeah,
questions.
so my point was that, so I don't know what drove the peak, but all I know is it wasn't the heat pumps, right? So I'm saying that the HVAC system, normally people think that the peak, that the summer peak condition is driven by air conditioning, but in this case, it wasn't true, right?
It was plug load from occupant activity.
It was occupants. It might have been the water heating system. Well, no, I covered that. So,
yeah, you
so
covered
the
that.
heat pumps and the domestic water heating system did not drive the peak of the
Right.
building.
So it was occupant activity with plug load.
I think it's people.
A lot of Netflix.
And
Your
so
second,
not to say that peak, and so not to say that the heat pumps were on and weren't high, but the peak moment was not driven by the HVAC.
Well, keep in mind they have
So-
electric stove. This is a fully electrified
Yeah.
building.
I think, is this a better way to say it, Hugh, is that the peak of the building was not coincident with the peak of the heat pumps.
That's correct.
It was not coincident. Certainly it was contributing, but it was not coincident.
Yeah, not perfectly coincident.
And that's a little counterintuitive to the way we think about
That's
daily
right.
and seasonal coincident peak load for a utility and the demand on a building.
Yeah.
Okay? And then you had a second question about open loop.
Yeah. So I called it open loop control, and this is my word. So what I'm saying is it's not a traditional system where there's a pressure sensor out in the building and the VFD on the pump is being controlled by that. The pump is just deciding by itself how much pressure it needs, and it's doing so. It's the other way to say it. It's sort of sensorless variable speed control.
But that's the trick, that's the art. Because the pumps know automatically by the back pressure, how many heat pumps are on and what kind of flow we need in the system.
And they automatically compensate then.
Yeah.
Correct.
So
We
it's
set them once, it takes about 5 seconds, you push a red button, and everything else is done automatically. It's fascinating.
You all are geniuses. This is
Not the moderator, the
Yeah.
other 3.
Just
Okay, last question. Go ahead.
quick one. What type of emitters are you using in the apartments?
What type of what?
Emitters, fan coil units, floor coils.
What type of air handling emitters?
They're heat, yeah.
They're actually heat pumps. I mean, every apartment has its little mini heat pump, usually a 3/4 ton or 1 ton. And so each apartment controls their own heating, cooling, temperature, everything else.
And they're ducted. They're
Yes.
ducted heat pumps with moderate ducting.
Yeah. And Toby, you had a question? Oh, it's methanol. It's methanol in there. This is why, and this is one of the reasons the pumping power is so low, because it's much easier to pump and transfers energy better than glycol. So we use an alcohol for that instead of glycol.
Okay, last comment, and then the sandwiches are waiting. I don't know what to do about those. Go ahead, Matt.
He is getting very impatient.
Matt, go ahead.
Factory packaged in there to help calculate the usage of the unit. Is that an option that will become more widespread, you expect in the future?
Are you talking about the data analytics capability of the units? It's a standard option today. Making that standard in all units is something to consider, but it's not included in all equipment today because of the cost. Okay? Great. The panelists will be available. Great job. If you haven't